we're talking about chemistry, we've already talked about how important balancing the chemical equation is, and and how essential it's going to be for the rest of the problem, right? So we know that the chemical equation kind of acts like a recipe for us. So have you guys ever baked a cake? Anybody baked a cake?
Yes.
So we know that when you guys bake a cake, the ingredients, if you bake it the way I bake it, you get the cake box, the box mix, right? You get some eggs, you get butter, milk, right? Is that how you guys bake it? Or am I just making stuff up?
Yes. Yeah.
Okay. Okay, so when we do that, right? Sorry, I just need a second to get my thoughts together here. So when we do that, we sit there and we think about it. Okay, so if we're gonna bake a cake, right? Let's say we have, how big are your families? Do you guys have big families?
Yeah.
Yeah. So my family, like my mom and dad all together. So my mom has 9 brothers and sisters. My dad has 12 brothers and sisters. And so when we have family gatherings, like real family gatherings, we have a whole bunch of people. So you're gonna have to, just the word that you want to build up. I can't even think of the term right now. My head is in so many different places, but we want to expand or to make larger the quantities that we need, right? To scale up, that's the word. We want to scale up the amount of cake that we need, right? So if I have a big family event, one little cake isn't going to be enough, is it?
No.
No.
And so if we think about this, a chemical equation is just like that cake and recipe, right? Because we know with a cake, if we write it down, we have, as I said, 1 box cake. How many eggs typically?
2.
3.
Okay, we got to go with Angie because I'm sure that she's made a cake recently. Okay, how much milk?
1.5 cups.
Okay, so how much butter?
I'd say 1 stick.
Whole stick.
That's right, at least 1 stick.
I don't know. I make pancakes, not this.
And we know that that's going to give us our 1 cake. Okay, so in the kitchen, we always follow these recipes. In the kitchen, we're kind of doing chemistry. And so we actually have basically made a chemical equation out of our cake. We need 1 box cake, we need 3 eggs, we need 1.5 cups of milk, and we need a stick of butter. Okay, so if I have family coming over and we're bringing everybody, so we're going to need about 50 cakes. So am I just going to take 1 box of cake and then add 50 eggs?
No.
Well, if I need 50 cakes, then how many boxes of cake will I make? I need
50.
50.
I'll need 50 because there's a 1-to-1 ratio, right? Yeah. If I need 50 cakes, how many eggs will I need?
150.
150.
150 because there's a 1-to-3 ratio, right? If I need 50 cakes, then how many cups of milk do I need?
75.
75. And if I need 50 cakes, then how many sticks of butters do I need?
50.
Okay, because there's a 1-to-1 ratio, right? So you guys see how that works with the cake?
Yeah, I see it.
Okay, so chemistry, it's no different. Once you got the chemical equation set up, you have it balanced, you have the perfect recipe, right? So if I have 4 molecules of ammonia, then I'll need 5 molecules to make these products. If I have 5 molecules of oxygen, I'm going to need 4 or I can make 4 molecules of nitrogen monoxide. And so we're able to sit there and establish these ratios with the coefficients in front of the chemicals that we're looking at, right? And so that helps us maintain that ratio so we can scale up or scale down as we need, right? So if I was making cake just for me, do I need to sit there and make a whole cake, or can I get away with making a smaller version?
A smaller version?
Yeah,
No, you're gonna have to make.
because I could get that egg, in the right proportion, right? So it allows us that flexibility, right? So we can go much smaller or we can go much larger. So we can scale up as needed, okay? And so that's the beauty of a chemical equation. You guys understand how it works? And I know that you guys have been doing it since the very beginning, so this is all same old stuff. Now we're going to see how to apply it, okay? If 3.20 moles of ammonia reacts according to the equation, how many moles of water will be produced? Let's put down that equation. Okay, so we have the chemical equation here. It says if we have 3.02 moles of ammonia reacting according to the equation, how many moles of water will be produced? So in this situation, we're always going to start off with our given. What is our given?
3.20.
And we want to make sure that we include our units, moles
Moles.
of ammonia. Okay, so what is the relationship between ammonia to water?
Where is everything about?
What is that?
I think his mic was just off.
Okay, we had a hot mic incident. So moles of ammonia to water. Are you there?
Yeah, I'm trying to figure out, so is this, because I think the homework assignments have this looking very confusing to me now, because it's making me want to bring in molecules and all that other stuff.
No, right
I'm
now
not-
we're just talking about moles, right? So moles,
Right, that's
we
why
know
I'm
that,
just like,
yeah.
Well, X moles to, I think, water. 3.2 moles of ammonia to X moles of water.
Okay, that's true. But
Okay.
according to the chemical equation, don't worry about what you're given right now. We already took that in consideration. What is the relationship between ammonia? So if I have how many moles of ammonia, how many moles of water can I make?
Well, according to the equation, if you have 4 moles of ammonia, you'd have 6 moles of water.
Okay, so we're going to use that relationship, right? So since there's 4 moles of ammonia, I can make 6 moles of water. So you're going to use your chemical equation to sit there and get that chemical ratio. So then this allows me to calculate the number of moles of water from the amount of moles of ammonia that we actually started out. Okay, what do you guys get?
So that would be the 4.8.
Okay, 4.8. How many sig figs should I have?
3.
That's right.
2.
3. 3 sig figs.
Of H2O.
That's right. Okay, so by using the chemical formula, right, that chemical equation that we sit there, we balance and everything like that, we can sit there and use to determine how much of something we can actually generate or how much of something that we actually need. Okay. Go forward. Okay, so this process is called stoichiometry, right? And so for stoichiometry, in a very general sense, what you're going to get, so you have particulate quantity of your reactant is going to be able to give us the particular quantity of product that we're going to make. Kind of like we're sitting there taking. If we have 1 box cake, we have 3 eggs, we have half a cup of milk, and we have 1 stick of butter, we can make 1 cake, right? And we can scale up appropriately. You guys see that?
Yes.
Okay, so when we're doing this, we're going to use quantity because quantity, or we're going to use moles, right? Because it's based upon how much you have, right? It's not going to be based upon the mass. So you're always going to want to change your mass into moles to be able to use the chemical equation. Does that make sense? Because the chemical equation tells me that for every 4 molecules of ammonia, I need 5 molecules of oxygen to make 4 molecules of nitrogen monoxide and 6 molecules of water. Okay, so it tells me in terms of that quantity, right? So we always need to sit there and change it. If we have grams, we need to change that to moles before we can use the chemical equation to determine how many moles of something we're making or how many moles of something we need. Okay, don't worry, I'll give you another example. Okay, so we have this equation here. It says, how many moles of oxygen are required to burn 2.40 moles of ethane? So first thing I want to do in this case is to do what?
Write the given of the 2.4 moles of ethane.
Okay, so I have
Write the
2.4 moles of
equation.
ethane. Is there anything else I need?
Write the equation.
I need the equation. So what is the equation?
C2H6 gas plus O2 gas yields CO2 gas plus H2O.
Is it balanced?
No.
Okay, what do we need to do to balance it?
So in front of CO2, restart.
Does that put a 2 in front of CO2?
Yeah.
Okay,
A 3 in front of the oxygen gas, and then a 3 in front of the water molecule.
okay,
That's gonna add out to 7.
okay. So
Still a little
7.
unbalanced.
So it's not balanced. So we have
Is this,
7.
are we gonna have to do the half thing again with this one or no?
Oh yeah,
well, I can't see the full screen.
you can't see the full screen.
Yeah.
You can move your
I can't.
you can move your image of everybody talking where that's at. You can minimize it so that.
Okay.
Did that work?
Still figuring that. Okay. Okay, yeah, it works. Thank you.
Okay, so it's not balanced.
Hmm.
So is this when we put the 7 and do the 2
Over
or
two.
Yes, yes, that's it.
Over 2, okay.
Yeah.
the ones I don't like?
And then we have to multiply everything by 2.
Yes.
Okay, so then we'll get 2C2H6 plus 7O2 equals 4CO2 plus 6 H2O. Okay, is it balanced now?
It is.
Okay. Okay, now that we have a balanced equation, we can start with our given. Okay, and what are we looking for?
See.
How many moles
Oh,
of ethane for
oxygen.
each?
So we're looking at moles of oxygen. At the end of the day, we want moles of oxygen. Okay, so what am I gonna do?
Are you gonna write the 7 ethane on the bottom with the 7 oxygen on the top?
You said 7 ethane?
No,
Two
2,
eth-
sorry, 2
Two ethane.
ethane on the bottom with the
Okay.
7 oxygen on the top.
Okay, so 2 moles of ethane on the bottom
That it cross.
and 7 moles of oxygen on top. Okay, so then this is going to cancel out. And then we're left with just our moles of
8.4. 0.4 moles of oxygen.
You said how much? 8.4?
8.4, yeah.
Okay, 8.4 moles of oxygen. Good, bad, or ugly? Simple? Not too hard?
Not so hard.
Not too hard.
Not too hard once we know what the setup is.
For me, it's hard when you balance, when no is balanced, it's hard, but the all is okay for me.
Okay. Yeah, so usually that's the thing that I always get to everyone is that balancing. So you always want to make sure that you get that done right and you verify. Right? Because we could have made that mistake and put that 3 there and that would have just done everything off. But Sal said, nope, that doesn't work.
Yeah.
Okay. Let me clear. Okay, so if you're given a mass, you always want to go to moles. And if you're so you're going to cancel out using the molar mass. And then you're going to use the mole to mole ratio. So moles of what you got compared to moles of what you want, right? And then if you want the mass of what you want, then you go back and you convert it back to mass using the molar mass of what you wanted. Okay, so this is just kind of like the pattern to go from mass to mass. Okay. So again, steps, if you're given a mass, you're going to use the molar mass to change to number of moles. Then you're going to use the mole-mole ratio from the chemical equation to get the moles of what you have to what you want. And then you're going to use the molar mass to convert back to the mass that you want. So one more time, just for those who want to see it visually, right? So if we're given mass in grams, we're going to use the molar mass to calculate the number of moles. Then from the number of moles of what we have to get to what we want, we use the mole-mole ratio. And then once we get what we want, the number of moles of what we want, we can change that to mass by using the molar mass of that product to give us the number of grams of what we want. Okay, now this could also work with the number of particles as well too. So if we're given the number of particles, we're going to be using Avogadro's number, right? And then that gives us the number of moles. So if we have the number of moles, we can go the same process and we can end up with the same number of particles. Are you with me so far? Okay. How many milligrams of nickel 2 chloride are in a solution if 503 milligrams of silver chloride is precipitated in a reaction of silver nitrate and nickel 2 chloride solutions? First thing I'm going to do is what?
Chemical formula.
Chemical
Yeah.
formula. Okay, so what is our chemical formula?
AgNO3.
AgNO3.
Aqueous.
Okay.
Plus NiCl2. Yields. Let's see. AgCl. Plus
Would the last
Ni.
one be NiNO3?
Okay. Anything else?
NO3 subscript 2.
Okay. Okay. What are the states?
Silver chloride is solid.
Silver chloride is solid.
And the nickel 2 nitrate remains aqueous.
Okay. So Michael, you had a question. It says, can you explain how you got that? Were you talking about the last problem? I think I lost him.
Yeah, I'm pretty sure he was. I saw the comment came up during the last.
Okay. Okay, so we'll after we do this, we'll go back and we'll see if that's the problem. We'll figure out what it is that you can get. Okay, or maybe you may be able to get it here, and then maybe it will apply it there. So, okay. So is it balanced?
No.
No.
Okay. What do I need to do to balance it?
Add 2 in front of AgCl.
Okay.
So add that 2 and the
Add
gaseous
2.
side in front of Ag.
Right here too.
Yes.
Okay. Is it balanced now?
I think so.
Yeah.
Okay.
Yeah, it is.
Good. Good. Okay. So what is our given?
The 503 milligrams of silver.
Silver chloride.
Okay, so we have 503 milligrams of silver chloride. Okay, so we have milligrams. And we're normally given things in grams per mole when we talk about molar mass. Is that true?
Yes.
Okay, so I'm going to show
We
you
change it
something.
to grams first.
We can change it to grams first. That's one possibility. Or I'm going to show you this real cool trick. What is the molar mass of silver chloride? And how would I calculate it?
You
Calculate.
for the atomic mass of each element.
Okay,
So it would be
so we have 1 Ag and we have 1 Cl. Okay, so what it would be? What would we do?
for Ag would be 107.87.
107.87.
And for chloride, it's 35.45.
35.45.
And these problems, can we round up the same way before, or no, you need to stick to the decimals?
You can round up, but you want to kind of be careful with that sometimes because it will throw your numbers off a little bit.
It's 143.3.
Is that right? Grams per mole. Okay. So I'm going to show you something real quick on the side. That's going to save you a lot of grief later on. So if I have how many milligrams are in a gram?
1,000.
Okay, so for every 1 gram, there's 1,000 milligrams. So if I have moles, if I have 1 mole, how many millimoles are in 1 mole?
Would it still be a zero?
It should be the same thing, right? Because milli just means 1,000, right?
Yeah.
Okay. So if I have something in milligrams, so cancel out these units. And now we have 1,000 is going to cancel out. We have the exact same number that we started out with. That's milligrams per millimole. Okay, so I can just sit there and leave it in milligrams and know that when I calculate the mass, it's going to be in milligrams per millimole. So I can use that same thing here. So is that number 143 going to be on the top or on the bottom? I'm sorry, I missed that. For some reason I have a hard time hearing
Is it the bottom?
the bottom. Okay. So 143.32 milligrams at the bottom. And that means we have 1 millimole on top of AgCl. And what is it that we want?
Milligrams of nickel chloride.
So we want milligrams of nickel 2 chloride. Okay, so what is the relationship between silver chloride and nickel 2 chloride?
So
1:2.
Okay, so for every 1 mole, or I'm sorry, 1 millimole, of nickel 2 chloride, I'm going to need 1 mole.
1 or 2?
Sorry, you're right, 2 moles of silver chloride.
You just said you weren't paying attention.
I'm just keeping you on your toes, that's all.
I see you're putting or is it millimoles?
It's millimoles, yeah.
Yeah. Why?
Because we did the conversion here, it will be the same and it makes it easier for us later on.
Okay.
Because they want milligrams, right?
Okay.
And why
Yeah.
go, if we're starting off with milligrams, why go through that
Mm.
hassle of going through and changing from grams to moles to grams to milligrams? It's just more work.
Okay. Okay.
Okay.
Yeah.
Okay, so then,
Dr. Henry, can you put that thing flat so it doesn't have those bowls?
what was that?
No, I'm trying to take a screenshot. It's just those bubbles were.
Oh, they're in the way. Okay. Okay, so are we done though? Because we want grams, we want milligrams to be exact. So what do we need to do next? If we look at what's canceled so far, what we've gotten rid of and the units that we're having left, we have these guys are canceled. These guys are canceled. And so right now we're just left with millimoles of nickel 2 chloride.
Yeah, but when
you started, Brittany?
yeah, no, because I'm looking at the whole millimole versus milligram and seeing like the difference in the numbers with it.
Okay, so how would I get to milligrams? What would I use? What did I use to go from milligrams to millimoles?
That's the part that's throwing me off because I thought we used moles and millimoles to get to the milligrams on the bottom already.
Yeah, we did. Right? So we use this. What is this number here? Number was what? The 143.32. What is that called again?
Unit, the molar mass?
The molar mass, right? So we're going to need the molar mass again. But we're going to need the molar mass of what?
In this case
molar
would
mass of
be
nickel.
Chloride.
That's right, of the nickel 2 chloride. Okay, so what is the molar mass of nickel 2 chloride? We have nickel, and how many chlorides?
2.
2.
Okay. So 1 times the mass of nickel.
8.693.
58.693. Okay. And then
35.45.
2 times 35.45. So that's going to equal 70.9. And that's a 7, by the way. So we add it together.
It would be 129.593.
And we know that we can use milligrams per millimole because we know that, oops, running out of room. Because we know that the thousands are going to cancel off on the bottom, so we can just plug that into our equation. Who's going to go on top? The 1 millimole or the
the 1 millimole because we
No.
want to.
The milligrams gonna go on top. The millimole's gonna be on the bottom.
Okay, that's right. The milligrams are going to go on top. And the 1 millimole is going to go on the bottom. And that's a nickel 2. All right. Okay, so then the millimoles cancel out, and then we're just left with milligrams of nickel 2 chloride. So what do you guys get?
Well, and it has to be 3 sig figs, right?
That's right, 3 sig figs. That's correct.
So would the answer be 4.54 times 10 2 or 10 1?
Let's see.
I'm sorry, 40. Well, yeah, it could be 4.54 times 10 2 or 45.4 times 10 1, right?
My answer was just 227.
Same.
Yeah.
I didn't get that at all.
So what I always do is multiply the numbers up top. So you have 503 times the 129.593, and then I do the division. So then it's divided by 143, and then you put parentheses 143 times 2. And so this is what I got.
Oh, I didn't see the 2.
You right here.
227.
Okay, so just 227, yeah.
Milligrams.
Of the nickel chloride, yeah.
Okay. Questions, concerns, Cash? Michael, are you there?
I don't see him in the participants list.
Yeah. I guess he got upset because I didn't answer his question. Gotta go. I'll catch up with him. Okay. Okay. So you guys should already know this part. We've already talked about it so much. You've done like 3 labs on it already. Calculating the percent yield. So percent yield is going to be equal to what?
I'm sorry, what was the question, Dr. Henry?
Percent yield is going to be equal to what?
The full percentage of whatever it is.
The actual yield divided by the ideal yield.
Yep. Or I always say the actual over theoretical, right? You guys remember from all the labs that you've done? Last 3 labs that you've done?
Yes, I always forget to multiply by 100, and I'm like, why is it so off?
Because you always forget to multiply by 100.
Yeah, I forget a lot.
Old age, you know, or Mary Jane, one or the other. Okay. So a solution containing 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. Barium sulfide precipitates. Calculate the ideal yield of barium sulfate. So what are we going to do first?
Chemical equation.
Chemical equation. Okay. So what is the chemical equation?
It's going to be BaCl2 Oh.
BaCl2. Liquid, solid, gas, or aqueous?
Aqueous.
Because we know it's a solution. Plus,
I know the Na part, the sulfate.
Alan.
SO4 with the -2 charge.
SO4 with -2 charge. So that means how many sodiums am I going to need to balance it out?
2.
Okay. Solid, liquid, gas, or aqueous?
Aqueous.
And what are we going to make?
You're gonna make BaSO4 the ClNa.
You mean NaCl?
Yeah. That's it. I go by that.
Okay. Barium sulfate, solid, liquid, gas, or aqueous?
Solid.
Precipitates lets us know that it's a solid. Sodium chloride?
Also solid.
Aqueous.
It's actually aqueous.
My bad.
That's all right. So we know that if we looked at on our periodic on the solubility table, we had chloride and sodium. It'll let us know that it's soluble, so it would be aqueous. Okay. Is it balanced?
No.
What do I need to do to balance it?
2 NaCl.
2 NaCl. Okay,
Snap.
balanced now?
Yes.
Okay, so now that we have it balanced, what are we going to do?
Calculate the ideal yield first.
Okay, we need to calculate the ideal yield. So how are we going to do that?
Mhm.
What's our given?
3.18.
3.18. That's grams.
The grams of barium chloride.
Okay. Okay, so what am I going to do next?
So we're gonna find the molar for the BaCl2.
Okay, so we need the molar mass of barium chloride. Okay, so how many barium? In barium
Only
chloride?
one and
One.
2 chloride.
And 2 chloride.
Barium's 137.33.
Let me say 137.33. This is times 2, 35.452. So then we add them together. We get, what's that? 208.
208.23.
Okay, that's grams per mole. Okay, so what are we going to do with that?
That's gonna be our bottom number.
Okay,
Cross off. Column.
208.33 is going to go to the bottom. That's grams per 1 mole.
It's 0.23.
That's going to give us a number of moles, right?
Yes.
Oh, sorry, 2-3, you're saying down here. Okay, my bad. Thank you. Okay, so then what's next? So now we have moles of barium chloride. What do we want?
Barium sulfate.
We want barium sulfate. How can I get moles of barium sulfate?
And that's something to do with how many is in each part, but I don't remember how to move forward.
1:1.
It's a 1-to-1 ratio, right?
Yeah.
So you have it balanced, 1-to-1. So we use that mole ratio, 1 moles of barium chloride to 1 mole of barium sulfate. Okay, so now we have barium sulfate. Moles of barium sulfate. How do I get grams of barium sulfate?
The same thing you have to figure out for BaSO4.
Okay, we got to figure out the molar mass for BaSO4. We have Ba, we know that that's 137.33. We have sulfate. That's what?
32.06.
32.06. And then we have 4 oxygen.
4 times the 6, 15.99.
Okay. I'm just going to round that one up.
Because that one's safe to round.
Yeah, that's a nice safe one to round. Yep. So that's what? 464. Okay. 64 plus 32 plus 137.
$233.39.
233.3.
But why did you get 48?
Oh, it's not 48. That's
4
4
times.
oxygens. My bad.
Oh, okay.
I was trying to make my little loop. 4 oxygens. That doesn't help at all either, does it? 4 O's. Okay. So, and that's grams per mole. So is 233 going to be on top or on the bottom?
It's going on the bottom.
Are you sure?
Wait. Why is it on the top?
233 grams. Oops, 233.3 grams of barium sulfate over 1 mole
Oh, the mole, I suppose. Okay.
of barium sulfate. So then the moles are going to cancel out. And we're left with just grams of barium sulfate. What do you guys get?
Eight 8.96317.
Get 8.9.
6317.
It seems like a little too much.
I got 3.56.
Yeah.
I got 3.56 too.
So if you go 3.18 times 233.3 and then divide that by 208.23.
3.56. 360.
grams per, grams of barium sulfate. Okay. Okay, so then that's the first part. So if I have the actual yield being 3.37 grams, calculate the percent yield. How would I do that?
That means get the actuals versus the other one and then times that, divide them and then times it by 100.
Actual over ideal or theoretical times 100. Okay, so we'll get 3.37 grams over 3.56 grams times 100. What did you guys get?
%94.7%.
Okay. 94.7%. Okay, questions?
How did you get 3.37?
That's given to us in the problem.
Oh, okay.
Okay. Questions? Concerns? Cash?
Real quick on the ideal yield, like I see obviously like the 3.18, but where does the 208 come from again?
From the molar mass?
Yeah, on the bottom, yeah.
The molar mass of barium and chloride.
Oh, okay. No, I can remember that now.
Yeah, it's hard to kind of remember the things you need in order to get rid of the last thing.
So I always say, if you're given grams, you always know molar mass, molar mass. Because I want to get moles and mass, molar mass. And then if I want to get grams from moles, same thing. I know I'm going to need molar mass. I just have to use it differently, the inverse of it, right?
Okay. If 5.9 times 10 to the 25th molecules of CO2 are produced in combustion reaction, what is the volume in liters of CO2 produced? The density of CO2 is 1.98 kilograms per cubic meters, and 1 liter is equal to 1 decimeter, or 1 cubic decimeter. So, where are we going to start with this?
Yo, can you start by telling me where it's at?
Number 27 of homework 8.
Homework 8. All right, thank you.
Your numbers might vary slightly. If any number is going to change, it's going to be this first one, but that's okay. The only thing that changes is the calculations a little bit.
Convert molecules to moles.
Okay, so if we convert the 5.9 times 25 molecules, CO2 to moles, how are we going to do that?
1 mole on top.
Oh.
6.022 times 10 to the 23rd on bottom.
Okay, and what is that
Yeah.
number called?
Avogadro's constant.
Okay.
Avocado's number.
Yes, avocado's number. Molecules of CO2. Okay. So now we're in moles of CO2. Now what?
Convert to grams.
Okay. How do I do that? What do I go through?
Use the molar mass of CO2.
So grams of CO2, 1 mole CO2. So molar mass, carbon is 12, oxygen is 16. We have 2 oxygens, so we're going to get 44 grams. Okay, now what?
Here, I actually messed around with the density before instead of messing around with the grams. So I converted density to grams per liter.
Okay, so it's probably a little bit more complicated, but it works. So did you add it into the same equation, or did you just do a separate equation?
I did it off to the side, but I guess you can just convert the grams to kilograms CO2 to remove a step from that one.
Yeah. So yeah, you could just convert grams to kilograms in our equation, which would be
Grams on bottom, 1,000.
per 1 kilogram. Okay. Now that we have a unit, kilograms, that matches our density, we can go ahead and use our density. So go 1.98 kilograms per 1 cubic meter. Okay. And how these problems are set up.
Wait, where you guys are right now, okay, the first half of the question I understand, even the kilogram part I understand, but right now where you're at with the 1 M3 and the 1.9, how did we get to this point?
Listed in the question.
Yeah, so we look at our question and we realize that we're given molecules, right?
Mm-hmm.
Which we can convert to, we can go molecules to moles, which are both quantities. Then we could go from moles to grams, which is a mass unit, right? Then somehow we need to get to a mass unit to a volume unit. And the only way that, or the easiest way that we can do that is to go through density. So density allows us to convert a mass to a volume. And they give us the density. So our goal is to take our mass unit, grams, and to convert it into a mass unit that matches our density. And in this one, it happens to be kilograms.
Okay.
Okay. And now we've converted kilograms to cubic meters, and cubic meters is going to be that volume unit. Now we're just working purely in volume, and we just need to get it to liters. And they give us a hint here where they say 1 liter is equal to 1 cubic decimeter. So that gives us the hint that we need to convert cubic meters into cubic decimeters. Then we can go from cubic decimeters into liters. Does that make sense?
Yeah.
Okay. So what is my conversion from cubic meters to cubic decimeters?
Cubic meter on bottom, 1.
Okay.
And 1,000 cubic decimeters on top.
Then cubic decimeters to liters is just a 1-to-1 conversion. So don't really need to add it, but I will. 1
For
liter.
visual, I'm gonna write it.
Yeah, exactly. 1 cubic. Okay. And now we just got a really long math problem to deal with.
Well, see, this is why I can get it. I think I had like half this problem and I was like, yep, nope.
Yeah, so a lot of these problems ends up just being one really long math problem, which is okay. We've been dealing with that the entire semester. What we're dealing with now, what students are going to get caught up on is this outline process, or like the mapping out process of what steps we need to take to get there. And how I solve the problems is I'll either mentally write it down. At this point, that's usually what I do just because I've been doing it for a couple of years, but you could actually write it down. You can write down what you have, what unit you're dealing with, and just try to see where we need to end up. So we know we need to get to liters, and to get to liters, we need to probably go through cubic decimeters because they give us that. And we can see, okay, cubic decimeters kind of lines up with cubic meters, which means we need to get to kilograms. If we could get to grams, getting to kilograms is just an easy step. So it's that puzzle aspect of this to be able to find your answer. Any questions?
Nope, so far I'm still wrapping my head, but it's making sense.
Okay. Yeah, all this comes with enough practice, so. Okay, then Brittany, if you scroll down a little bit, there's a better written procedure of what we just did. If you can't read my handwriting, it's down there. Michael, is a lot of this on the exam? Yes, stoichiometry will be a big portion of the exam. So will the ideal gas law, the PV equals nRT, knowing how to manipulate that to get your answers. That'll also be a good chunk of your exam.
Oh, I have a quick question.
Yes, Catherine.
I just want to clarify, he said the project is due the 17th, right?
Let me check the calendar.
Because it still says on Canvas that it's the 14th, and I'm not sure, just the date hasn't changed, or?
I'll change the date if it still says the 14th, but yes, I believe your projects need to be submitted by the 17th because you're going to be presenting from the 18th through like the 20th.
Okay, thank you.
Or the 21st.
Cole?
Yes, Alan.
The same question that she just asked you, one of my group members sent a message on the group chat saying like the CHEM page that I guess it's due today, which is part of the project. Is it actually due today or it's part of what's due on the 17th?
I will.
He said everything was due on the 17th. He just hadn't had time to adjust our like grade books and stuff.
Yeah.
But he said it, and I asked him this weekend too, because I have someone in my group who's from at a different campus, and I had to call him because she was, spazzing and scared. And then he said the same thing to me this weekend when I called on Sunday because it was an emergency.
Yeah. So assume everything's on the 17th. But you can ask him during the lab when he shows back up.
Okay then.
Brittany, if you
I'm gonna
want
stop sharing. So yeah, everyone, if they want to take a screenshot of that bottom thing, someone knows.
Okay. So 5.31 gram sample of a compound that contains only hydrogen and sulfur was combusted and yielded 10 grams of sulfur dioxide and 2.81 grams of water. The molar mass of the compound was 68 grams per mole. What is the compound's molecular formula? Okay. Naomi, what do we need for lab today? Does someone wants to type it in chat? Because I don't know. Okay. So where are we gonna start with this one, guys?
would you start with that, whatever this like equation is?
Mm-hmm. So we need to figure out the equation. So if sample of compound that contains only hydrogen and sulfur was combusted,
Says that H2 gas plus
what was that?
would it be H2 gas plus
Not
gas?
quite. So if we're dealing with combustion reaction, right? We know for a fact that we're gonna have plus O2, right? And it's saying it yielded SO2. And it yielded H2O. All right. Then we have a compound that was combusted that only contained hydrogen and sulfur. But we don't know the amount that those contained. So we're just going to supplement X and Y for those for right now.
Oh, so would you balance this with knowing that information then to get the numbers or no?
We can't balance it because of the variables, right? Because those variables tell us how many of hydrogen and how many of sulfur are going to be on that side. Actually, hold on. Text Doctor.
It's definitely.
Yeah, because this problem is going to take like 20 minutes for me to fully explain it. So let me text Dr. Henry and double check that we have lab right now. Then if we do have lab, I will go over this problem right away in my tutoring session. And if not, I'll write it out and send it to you guys. Because there's usually a problem like this on the exam, but usually deals with a hydrocarbon. So it's going to take 20 minutes on a test. No, it'll probably take you like a good 5-6 minutes on the exam for a problem like this. But if this is your first time seeing a problem like it, explaining it takes around 20 minutes, unlike the process that we do. But there is kind of a cheat. And you know, I was once a student, so we all love cheats. So if this is a multiple choice question, right, as it is on here, and we know that the molar mass is 68 grams per mole. And since we're specifically looking for the molecular formula, which is the complete formula, not the lowest term formula, what we can do is we can see which one of our options is going to add up to 68 grams per mole. So H4, 4 hydrogens, is going to be 4 grams per mole. And what does sulfur weigh for its molar mass?
3206.
Is it 36?
3206 times 2.
Dr. Henry said lab will be starting at 2:45.
Plus 64.12.
So, right. So sulfur is 32. It's 32, which just equals 64 because it's 2 S's, which is going to get you that 68 grams per mole. Right? But we could look at all the other ones. Hydrogen is only going to give us 2 plus a 32 for that sulfur. 1 plus 32. Then this is going to be 2 64. So we're in college, gotta work smarter, not harder. if you know other ways to solve it,
Definitely.
works the best. But don't use this as the main method. There's a couple things that needs to happen. It needs to be a multiple choice question because you need multiple answers to help you. And you have to be looking for the molecular formula. Because if it's not the molecular formula, then it's going to be the empirical formula, which needs to be in lowest terms. So you're going to get a different style. But
Oh
if
my
you guys, yeah, so we avoided all this fun math that we can do. But I'll explain the math process since we have a bit of extra time. But like I said, you guys are more than welcome to head out if you want. Class is officially over. But so what we're doing is we're looking for an unknown compound known as HXSY. We don't know what those variables are. So we need to see what is being yielded because we know that we can't just create atoms out of nowhere. They have to come from somewhere. So we're going to see how many moles of hydrogen are going to be produced in our reaction and the moles of sulfur that are going to be produced in reaction. We don't care about the moles of oxygen. Why don't we care about the moles of oxygen, even though it's a combustion reaction?
Because it's not in the final, like what we're looking for at the end.
Right. It's not in the compound that we're looking for, right? Even though it's in everything else, so H2O plus SO2, it's in everything else. It's not in our initial compound that we're looking for. So we don't need to take into consider oxygen. Sometimes you're given like a hydrocarbon with oxygen and you have to worry about it, but that's again, not part of this. So we just want to see how many moles of hydrogen we have and how many moles of sulfur we have that we produced. Okay, then we need to determine how many moles of the initial compound that we had. So we were told that the compound, or we have 5.31 grams of the compound, and we were told that its molar mass was 68 grams per mole. So we could find out how many moles of this unknown compound. Okay, and now all they did down here as the last step is they just made a ratio. They said, so they're just saying, okay, so 0.031 9 moles of H divided by how many moles of the actual compound we had. Moles of compound. So if anyone wants to actually divide those two numbers. What do we get?
You get the same amount like that, just not with it being 4.4, blah, blah, blah.
Right, we get roughly the 4.0, whatever, but we didn't cancel out any units. So that's why it still says moles of H over moles of the compound. They're telling you how many moles of hydrogen are in that compound. But let's just say for practice sake, since we already know our answer, the cheating way. Let's say that for some reason we got 4.7 moles of hydrogen. And the other one we got just 2 moles of sulfur. In a compound, can we have hydrogen 4.7 sulfur 2.
No.
No. What do we do if that's what we get?
Just like how we do with the half. We would multiply the whole thing.
Yeah, we would multiply the whole thing just so that we can get it to a whole number without a decimal. So, right, Michael, it's not a cheating way, it's just a way to check your work. That's why I told Dr. Henry when I did it as well. So that's the whole process. That's what all this math is for. But like I said, test situations, if you only have like 4 minutes left and you have like a couple problems, you got to know some workarounds to avoid a lot of math.